Is everybody having fun at the conference? Raise your hand. Yeah. Everybody learn like some new stuff? Anybody's, mind explosion thing going on. We'll go ahead and get started. I'm William Harvey. I'm a principal engineer at a company called OCLC out in the middle of Ohio, with all the cornfields and the cows wandering around, eating things, ruminating. Thank you for coming to my talk. Today I'm going to be talking about metaphorisms, deriving divide and conquer recursive programs from relational specifications. This is not work that I have done per se. This is some work by another PhD across the pond, but I felt that I would be a good test pilot for this idea. But first I would like to just touch a little bit on this notion of fear in our industry. So it's kind of funny because software is like one of the most low stakes things we can possibly do for a living, right? So it turns out that there's a neural circuit in our autonomic nervous system that plays a big role in our experience of fear, right? It's like an old imperative code base that was written into our biology, 500 million years ago by some Cambrian fish. And it turns out there's a way to diffuse this. It's called a vagal brake, and it's induced by laughter. So when you're out trying to gain adoption for functional programming at your organization, business, whatever, try to make people laugh, try to make them smile, keep them relaxed. And it turns out that metaphors are a great way to do that. So without further ado, let's start playing with some metaphors and see what they can do for us in a programming setting. So this talk is heavily based on some very interesting work by Dr. Oliveira here on metaphorisms, which allow us to formulate our program specifications by mimicking the categorical structure of linguistic metaphors. Once we've done that, there's a formulaic way to derive a functional program from that specification using something called the algebra of programming, or the Bird-Meertens formalism. Has anybody ever heard of this before? Yeah, it's almost a cottage industry type idea. So I had this funny thought that maybe Dr. Oliveira and I both submitted an abstract to present on this, and due to the double-blind selection process, my talk was selected over his, and I think that would just be a complete and utter disaster. So if that's the case, whoopsie. So like I said, I'm not entirely qualified to give this talk per se, but I did race through this idea and try to apply it to what I was doing. I wanted to see if it could make my life easier. And the answer is, it kind of did. It got me into recursion schemes. Does anybody know what recursion schemes are? Got a chance to play with them? That's awesome. So I got a little bit of a head start on those. Another thing that I gained from looking at problems this way was, as a programmer, I'm always thinking in terms of functions, right? There's inputs and there's outputs. And data flows in a certain direction, right? And you can't go back. But if you relax that a little bit and you start working with general binary relations, there's like no notion of flow, right? You can go forwards and you can flow backwards too. So I thought that was really cool and mind expanding. So for this talk, I'm not going to be presenting Dr. Oliveira's work in its full generality. I'm going to be specializing it down, trying to simplify it, okay? And focusing on a few key concrete examples that I think should be familiar to most of us, like sorting algorithms, string formatting, that sort of thing. So if you find this stuff interesting, I encourage you to go look at his work, because he's the genius, not me. So first, I would like to give you a little bit of an overview, just because, we're all going to have to go home and try to get FP adoption at our businesses. So I want to show you how we're using it at OCLC. Then I'd like to introduce the research problem through which I came about discovering this metaphorism abstraction, right, and trying to apply it. Then I'll actually introduce what this is, and then I'll give some examples. So my company is called OCLC. We help libraries do things. Academic libraries, public libraries. We are a nonprofit. We're also a global library cooperative. We have thousands of library members in more than 100 countries. We have a big old database called WorldCat, which happens to be the largest online public access catalog in the world. And we maintain and own the Dewey Decimal System. Yeah. So that sounds kind of dry, but here's something cool that we did this last year. Well, we, meaning mostly me. This is a library-friendly visual analytics dashboard written in 100% Scala, even the front end, via Scala.js. Number of people who worked on this, 1. Number of defects in the last year, 0. 0 defects. Functional programming.
Number of users?
I was waiting for somebody to ask that. Exactly. So what's the secret sauce? Free applicative functors, bidirectional parsers. The producers and consumers here, they talk Vega Lite, which is it's a visualization grammar which makes these pretty pictures on the right. The UI tools are all wired together using functional reactive programming. So the end result is like there's no places for bad things to sneak in. It's all just, it's airtight. It's amazing. I also used category theory to design the drag and drop interface, because not only can you use category theory to think about programs, but you can think about it, you can use category theory to like model anything. It's a really versatile tool. So here's another cool thing we did. This is another visual analytics dashboard. We do a lot of this kind of thing. This is sentiment analysis via document embedding. This tool allowed us to take thousands of these documents that were derived through research studies. They were basically interviews with people, and we could splat them into this space and just start poking around in there and seeing what people are saying and how they're feeling about things. So we're doing a lot of exciting work. We do big data modeling. We use cool mathematical thingies, groupoids, torsors, all this stuff. We make DSLs. We do information geometry. That's my bread and butter. That's my area of expertise, not programming languages. And we're just starting the FP journey. So if this stuff sounds cool, come talk to me. It's a nonprofit, so if you have student loans, you can get those forgiven in 10 years. So here's our motivation for using metaphorisms. We had this research project where we wished to better understand how our users were interacting with our search engine. Our search engine is called WorldCat Discovery. It's just plain old search engine. So we needed to do some kind of behavioral or clickstream analytics, right? So we wanted to find out what our users were doing and how we could help them do what they were doing. Who here has done like server log analysis, that sort of thing? Yeah, okay. So you know that sometimes you get terabytes of text data sitting around, okay? For our study, we were able to throw away lots of our terabytes of data and just focus on a core 100 gigabyte data set, okay? Now, here's the thing that like rubbed me the wrong way. So there's 100 gigabytes of text data, but if you compress it, it goes down to 5 gigabytes, right? Massive amount of redundancy in there. So, as data miners, data scientists, whatever, you want to do some kind of exploratory data analysis, right? So what do? Do I take that 100 gigabytes of raw text and stuff it into Logstash or Elasticsearch just to explore it? Or is there something more intelligent I can do? I thought there was something more intelligent I could do. So it turns out there's this really, really cool thing called succinct that these folks from Berkeley came up with. And this was a game changer for us. This allowed us to play around with that 5 gigabyte compressed data set. Actually, it inflated a little bit, but it was still pretty small. It definitely wasn't 100 gigabytes. So what is succinct? It's a compression format for unstructured text. And it allows you to query this compressed text directly. No data scans, no secondary indexes, no data decompression needed at all. It's really cool. Go check it out. You lose a couple things. The pre-processing, the compression part, is expensive. It uses some CPU to actually access the data in there. And sequential scans are kind of slow. And it's like, there's no way to update it. It's read-only, so it's for analytics. But still, it's really cool. There's the URL. It gives you all these really cool operations you can do on your big, yes? Yes, yeah. It's just like working with a plain old string, but it's compressed. And you also get all of these operations in sublinear time, which is amazing. You can find all the instances of a string. You can count them. It's really cool. So we wanted to use this for our research project. Problem is, we didn't have this algorithm and data structure available for our tooling in our programming environment. And the open source version maxes out at 4 gigabytes, which is too small for us. So we had to try to implement this stuff from scratch. Who here implements algorithms from scratch very often? Yeah, I've done this hundreds of times throughout my career. It's crazy. You get the academic paper, you pour through it, there's pieces that are missing, pieces that are inaccurate, you have to think really carefully, and it's nuts. So we had to reinvent the wheel. So we decided to build one of these ourselves. There's two ingredients. One of them is a compressed permutation data structure. You have a list of integers, you permute the integers. It turns out that you can take advantage of some consistent patterns in that permutation to use less space than just a list of integers, which is pretty cool. And the next slide, I'll show you the book. The other thing is you need a suffix array algorithm. This is something that people use in bioinformatics a lot. So I was brave. I implemented the first one from scratch. That's what I do. And the suffix array algorithm I wanted to implement was called DC3 or skew. It's a really clever algorithm. It's pretty simple. It's a divide and conquer type algorithm. When I saw that it was divide and conquer, I was like, I bet I can do this in functional programming style, right? Because we're very good at divide and conquer. And not only that, I was like, maybe I can throw this off at a computing cluster using Spark, right? Like MapReduce kind of thing. So I was thinking like, there should be a better way to implement this algorithm than reading the paper and writing an imperative version. So it turns out there's this whole field of research called program synthesis. And the idea is you write a spec for a program that you want to have, okay, that embodies the desired behavior that you want. And once you do that, there are semi-mechanical ways to extract a program from that spec, okay? Some examples of this are like when you write code in Coq or Agda, you can write all the proofs and stuff, and then you can actually extract a program from that and run the program. There's also ways to write models for a program that don't necessarily give you a way to extract. One of the most popular, well, I shouldn't say popular, well-known tools is called TLA+. Has anybody heard of that? Yeah, the people at Amazon supposedly are using this. So it's really cool. It exhaustively checks your model, but you can't extract a program. You have to write it yourself. But it turns out there's a way to kind of get the best of both worlds as long as you're like smart enough and dedicated to read on this stuff. It's called the Bird-Meertens formalism. This is a categorical calculus of relations. What does this mean? We're working in the category of sets, so we got a bunch of sets all over the place. And the morphisms between our objects, between our sets, are just binary relations. Okay? So all of us are hopefully functional programmers, so we're used to those morphisms being functions, right? But if you relax those functions a little bit, just put relations in place. And that's all this is, categorical calculus of relations. The authors of the Bird-Meertens formalism, who are Bird and Meertens, they used category theory to make their whole process language agnostic, right? They didn't want to commit it to one programming language. So jokingly out in the community, this approach is called squiggle. Okay. Relations are more flexible than functions, so it can be easier to work with. And the calculus part of it makes it formulaic. So after a certain point, you're just applying algebraic rules to your specification, and it's just slowly turning into a program. And you can prove things in it. It's a mathematical language. Prove properties of your programs. So the input is a relational spec. You encode the behaviors you want to get in your program, and you do this step-by-step derivation via algebra. And the output is a functional program. That's pretty cool. Here's a book you can read if you're interested in this sort of thing. Here's a whole bunch of problems they solve, not problems, but different kinds of algorithms they show you how to use in this book. It's really worth looking into. And you're also going to look at it and do a lot of head scratching, because we're used to looking at function signatures. F goes from A to B. They flip the arrow around. They put the A over here and the B over here, and the arrow's going this way. And there's a good reason why they do that. Because if you think about like function composition, we're always saying F after G. But if you reverse the things, then you just butt the functions up against each other and they compose naturally. So it's a clever trick, but it's these little things which make it a little bit inaccessible. Here's some proof that this Bird-Meertens formalism is actually useful. The authors of this paper devised a novel algorithm for the maximum segment sum problem, and they also proved something called the sliding tails theorem. So it's useful, but it probably hasn't caught on so well because it turns out working with relations is a lot more complicated than working with functions, because the additional degrees of freedom means you have like this Pokemon type environment where like you take a couple of Pokemon and you get something totally novel. With functions, it's a lot more locked down, right? Like you compose a couple isomorphisms and you get an isomorphism. There's a lot fewer rules to keep in your head. Another thing too is this is specified all in category theory. So like somebody like me wants to sit down and bang out a program in Scala, I have to now know category theory in order to, use this stuff. So it's a little tricky. Another thing too, so you'll be reading this book on algebra programming, and it's going to walk you through these proofs step by step, and you're going to be like, okay, yeah, that's really simple. And then you're going to suddenly see Leibniz, and you're like, I don't even know what that is. It's a guy. You go to Wikipedia, it's a guy. He was a famous mathematician. But there's some proof rule in there that is called Leibniz, and I don't know what it is. So, what are metaphorisms? These are Bird-Meertens formalism-style relational program specifications defined over inductive types, recursive types, like the ones we use in Scala, okay, Haskell. And the structure of these mimic formal metaphors, like the ones we use in everyday language. For example, time is money. All the world's a stage. William Shakespeare said that. A monad is a burrito. Noticing a pattern here? We're taking two things, two supposedly unrelated things, and we're saying they're actually the same thing because they're related somehow. That's the little funny trick. Monads are trees with grafting. That's another one. Some say love, it is a razor. I was going to make a joke about a chord data structure and a dysfunctional vocal cord, but I should have just not made the joke. Okay, metaphors in software. We use metaphors all the time in software. Trees. They're not actual trees, but we call them trees because they have a lot of similar properties. Pipes, stacks, heaps, queues, spaghetti code. And our favorite one, the bug. There's a wonderful book called Metaphors We Live By. Turns out metaphors are absolutely pervasive in our experience, our human experience. Just like the adjunctions in everyday life, once you're trained to recognize these metaphors, you'll notice them everywhere, especially while I'm giving my talk. And life will never be the same for you. These are pretty much our reality. Now here's something interesting, and this is just me speculating, but I think that metaphors are critical to learning intuition behind things. So most of us have been non-FP developers at some point in our lives, right? So we understand that we didn't have an intuition for a monad or an applicative or a traversable, right? So this might explain the outcropping of these monad tutorials that try to rely on some kind of metaphor to transmit the meaning of a monad in terms of concepts that are more familiar to us at a given time. Just a thought. So what is a formal metaphor? It turns out you can boil these down into three components. The first one is what's called a tenor. Okay, for example, love. The second one is a vehicle, a razor. And we're going to try to say these are the same thing, right, somehow. And how do we do that? Via a shared attribute. Ouch, right? So love can be painful, a razor can be painful. Love can cut you, a razor can cut you, right? And here is an interesting quote. Love is that you are the knife which I plunge into myself. Quote by Franz Streaming Kafka. Now there's a little bit of confusing stuff here. So I've been talking about metaphorisms and now metaphors, and now we have Franz Kafka's The Metamorphosis, okay? And it turns out there's something called a metaphorism, which is a recursion scheme, which is a fold followed by an unfold. So all this terminology is very Kafka-esque, wouldn't you say? Although Kafka had nothing to do with it. Categorically, a metaphor begins with a co-span in the category of sets. What's a co-span? It's something that looks like a bird flapping, okay? There's just something in the middle and two morphisms going out, but the morphisms point this way. That's just a categorical co-span right there. So here, F and G, those are functions. Those are morphisms in the category of sets. These functions just extract from the tenor in the vehicle the shared attribute. So the witty power of a metaphor comes from two features. The first one is to imply that the tenors are the same thing as a vehicle. And the way you do this is you start in the upper right corner, you follow G down, and then you go backwards through F. Okay? This, if you were to read this in English, it'd be where there's a vehicle, there's a tenor. So in a moment, I'm going to explain what it means to go backwards through a function, because you can't really do that, right? As a programmer, we know you can't go backwards. So don't let it stress you out too much right now. The second feature of a metaphor is to leave part of the metaphor up to the imagination. So by not spelling out the shared attribute explicitly, you let the listener stumble upon it themselves. And the listener feels very clever, and they go, aha, and they usually laugh, right? Or have a light bulb, or they guffaw, that sort of thing. That's the ingredients of a metaphor. That's it. Look for this pattern everywhere. Here's a concrete example of a metaphor that's kind of humorous. This is Mark Twain. Politicians and diapers must be changed often, and for the same reason. Okay, ha, right? We can pick this thing apart, the algebraists that we are. Here's the tenor of the metaphor, politicians. And we wish to say that the tenor is the vehicle. Where's the vehicle? The diapers, right? We're trying to say politicians are diapers, but we're not going to actually say it. We're just going to imply it. Okay, now where's the shared attribute? If you remember, it stays hidden. We hide it for the comedic effect. Well, yeah, we say like there's a hint, there's the same reason why they're, related. And then we give a little bit more of a hint to the listener. They must be changed often, okay? And I looked at this initially and I was like, well, what is that shared attribute, right? And I came up with something which is really mild and PG. Turns out there's another thing you can take away from this, which is quite vulgar and very funny. Being at capacity, let's just put it that way. So here in our categorical diagram, we have the set of all politicians and the set of all diapers. The functions f and g extract the attribute that shall not be named. We construct the unique morphism f converse after g. That's the thing going across the top that implies that politicians are diapers. And then we just hide the shared attribute from the listener, alluding to it just enough. And then the dominoes tip over in the listener's mind. 2 and 2 are put together, and the aha, this is clever remark is achieved. Okay, both must be changed often and for the same reason. I hope I didn't ruin humor for everybody. So let's take a little interlude and talk about function converses. Okay, and more generally, relation converses. Just to skip ahead, this just means a binary relation, you can flip it around for free and flip it back. That's fine. A function, you can't always flip it around. A function doesn't always have an inverse, right? So let's start thinking about the definition of a function. A function just maps each element in a set, say A, the thing on the left, to exactly one element in another set, B. Here's an example of one possible function from A to B. We'll just call it f. Does this function have an inverse? Yeah, it doesn't. If we flip around the arrows, we can see that that guy in the lower right corner goes to 2 guys on the left, and that violates the definition of a function. Okay. So what can we do about this? Well, it turns out that if we just forget about functions and say, we're just working with relations, it's totally legit. And that's what the little circle thing means. That's, you pronounce that converse, which means you're just flipping the thing around. Okay. So, who here has used SQL? Okay, yeah, relational databases, right? Relational model. We don't have to think about anything. We just join things together and magic happens, right? The query optimizer takes care of all of our needs. Well, that would have been wonderful. But, I'm wondering if these two terms have common etymological roots. In the upper left, we have SQL, and down here at the bottom, we have sequela. SQL is our query language, and sequela is a condition following and resulting from a disease. Okay, there's a metaphor here. Do you see what it is? I'm implying that they have common etymology when they actually don't. Okay, I'm hiding it from you. So let's work through a concrete example of building a relational spec in the form of a formal metaphor. And we'll start with text formatting. What does text formatting do? Well, it takes a string and it splits it across lines in a real nice way, and then it puts the white space in there in just a way that looks all nice to you. Okay? Some examples of this are like applying word wrap to a string, using Scalariform to format your Scala code, Go format, all that sort of thing. So as we build this spec, we're going to have to first pick the hidden attribute that must be preserved through this function, some kind of invariant, something that flows from the inside or the beginning to the end and doesn't get disturbed. The other thing we're going to have to do is realize that there's lots of ways to satisfy that invariant. You know, there's lots of things that are going to share the same hidden attribute. So we'll have to have some way to choose among many of those possible outputs in a way that works best for us. Let's just start by kind of reading this in English. So this part is like a formatted string is a sequence of strings that contains the same sequence of words as the input. Okay, that's what these morphisms are doing, these functions in this case. They're just extracting the words from the input string, and they're extracting all the words from the output list of strings and making sure they're the same. Okay. The next thing we got to do is, among all those possible outputs, we have to choose the one we like the best, because there's zillions of ways to format a string, right? Let's poke around point-wise to see how this works. So first we're going to flip around this function, because we can, if we treat it like a relation, by taking its converse. That's the green arrow here. It's totally fine to flip it around. This is really liberating, right? And we're going to just put a string through this green path here and see what happens. If we consider the input string here, foo-bar baz on the right. By the way, who's thrown off here that all the inputs are on the right and all the outputs are on the left? That's a squiggle thing. Yeah, I got that from the algebra of programming, so I apologize. I've just gotten used to it. Okay, so consider the input string foo-bar baz on the right. The output of the words function, of course, is the three words foo, then bar, then baz. Now let's compose that with the bind words converse. And what do we end up with? Unfortunately, we get an infinite set of string lists. And each string list in that set contains its own unique distribution of white space for whatever purpose. So the progenitor of this work, Jose Oliveira, states that if we can define an endo relation on that set, you know, all those possible string lists, that helps us choose which of those we like the best, we can plug that endo relation into our diagram that we've seen before, and in principle we can then, you know, derive our program out of there. So just to, you know, use a nice name, because naming things is so easy, let's call this endo relation better. And it's shown in blue here. Given a list of strings, it hands us back a string that is formatted better according to our formatting preferences. Finally, the last thing we have to do in order to finish the specification is introduce this blue arrow in the upper right corner. And you'll look at that and you'll be like, okay, it's just function composition. And then you see this funny half arrow thing, that black thing up there. What is that? It's this shrinking operator that Oliveira introduces, and you pronounce it shrunk by. So the way this works is it's this function or this relation shrunk by that one. And what does it actually do? Well, if we consider the relation that's on the left side of the shrink operator, we take its output, then that pipe is kind of like a little filter that makes the whole thing emit the best possible output according to the criterion on the right. So you can think of it as a quality control filter. So this thing over here is your little quality control filter, and this is your function which just spits out everything. This little guy just pipes it through a filter. That's what it does. Fortunately, that little guy is going to go away when you actually extract the program. But for now, it's there. Okay. So what does the spec for our format function here mean? It optimizes the white space while preserving the word sequence. That's the meaning of the metaphor. Okay. So when the objects in this diagram are represented in your favorite programming language as inductive types or recursive types or pattern functors, then Oliveira calls this pattern a metaphorism. That's a metaphorism. That's what this talk is about. And the promise is that assuming that you can get all this stuff right, the algebra of programming will allow you to formulaically, mechanically extract a functional program that does everything that's in this diagram. That's the promise. So it turns out that, like, in practice, there are some algorithms that aren't that simple. Let's go back. This is text formatting, right? Like, text formatting it has a certain shape to it, right? Certain kinds of operations you do. But think about like sorting or some algorithm where you have to find the fixed point of something, or I don't know what, okay? There's a lot of different shapes. So I'm going to focus on how to encode divide and conquer algorithms in this metaphorism structure.
Could you repeat what better itself was?
Yes. So this is a funny thing. It takes a thing and it gives you back a thing that's better than the thing you put in.
So as you would iterate that, you would eventually reach a fixed point or something.
That's kind of the idea, yeah.
So it's an improvement morphism.
Yeah. It can be.
Some kind of gradient descent.
Sometimes. Other times it cheats, and let's take sorting for an example. You pass in an arbitrary list, and it just gives you back the sorted one. That's it. So it doesn't always iterate, you know what I mean?
Yeah, I just meant eventually you'll reach an item code or something.
Yeah, fixed point, yeah. So there's a nice way to do divide and conquer algorithms in this setting. And to do this, we have to do two things to our previous diagram. The first thing is we introduce an intermediate inductive type right in the middle of the diagram, and that's going to be the cream filling in the middle of the divide and conquer Oreo. Okay. Anybody who's like really comfortable with those recursion schemes is going to see this as the virtual data structure that sits in the middle of the hylomorphism, and you don't actually see it. That's what that thing's going to do. The second thing you have to do is then express the divide and conquer in a form of a hylomorphism. So the actual morphisms you're going to put in your diagram, the implementation of those are going to be, catamorphisms and anamorphisms. And you're going to stick those together, and the whole thing's going to form a hylomorphism. The first thing we've got to do is introduce this auxiliary type W. This is going to be produced by an anamorphism and then consumed by a catamorphism, hylomorphism. The next thing we're going to do is go from V to T through W. That's where the divide and conquer thing happens. We have at least a couple of canonical ways to do this. This is what I thought was really cool about this work. And it's been observed before by other people, but it's really explicit here. There's like two ways to do this, two primary ways. The first one is easy divide, hard conquer. So for this formulation, the catamorphism H up here, it's usually a super straightforward conversion between types W and V. Okay, it's just totally brainless, does the obvious thing. And all the hard work of preserving the invariant and doing the optimization, that goes into the morphism Y here. That's where all the actual hard work happens. And the cool trick about this is Oliveira gives us a formula for dictating what Y should be. So once we discover that we can, formulate our algorithm like this, our spec, then there's a formula for figuring out what to plug into Y, which is pretty cool. When you think about this one, like your mental model could be merge sort, right? Dividing the input list into parts is really trivial in merge sort. But the conquering step requires a careful merging of sorted lists. That's why it's called merge sort, I guess. So the other canonical method is what's called hard divide, easy conquer. In this setting, we expend a lot of effort in the dividing phase by representing it as an inductive type W via anamorphism through some heavy-duty relation or function X. This is just like the other one, but the hard work is pushed to the conquer phase. And Oliveira also gives us a formula for this too, which is pretty cool. So if you can read the paper, which is a little challenging, there's actually several papers, but if you can get through that stuff, you can use this and relax. So when you think of this, you can think of quicksort a little bit, right? So partitioning a list in quicksort requires some careful considerations, right? You have to choose the pivot just right, okay? But once you do that, the actual merging is trivial. It's just, there is no merging, right? So that's the cool thing about it. So since we've been talking about sorting, let's go ahead and work through an example of sorting a list. First, we assemble a relational specification for sorting in the form of a metaphor. Then we show how to transform that metaphor into a functional program using our recursion schemes. So here's the basic type signature for a sorting function. It just transforms a list into a list, sorting along as it goes. So what is the shared attribute of our metaphor? Well, sorting preserves the elements of a list, right? A sorting is just a permutation of an input list. So we encode this by showing that a list and its sorted doppelganger on the other end should be equivalent under bag semantics. So a bag is like a list of stuff where the order suddenly doesn't matter. Okay? So the bag 1, 2, 3 and the bag 3, 2, 1, they're actually the same thing because they have the same elements in them. So if we move across the top morphism there, when we convert a list to a bag and then we go backwards through the bag function, we get all possible permutations of a list. So our next task is going to be to winnow that down a little bit. Our optimization criterion has to redirect each unsorted list to its sorted self. So how do we squeeze this into the diagram above? Well, I think the natural thing to do is to just plug in a predicate postcondition. What does this mean? It means we want to take a list and we just want to have a simple Boolean valued function that says, is this list sorted or not? Okay. But if you look at the question marks up there, that's different than list to bool. Here we're forced to put in a list to list. So like, oh gosh, how do we do that? Well, it turns out there's some kind of clever trick to do that, and I'm going to show you how to do it. So here's the upper left part of that diagram into which we want to stuff our binary predicate to check for whether or not a list is sorted. First thing we do is we put the little Boolean set up there in the diagram. That's just a set with two elements in it, right? True and false. And we'll introduce this function order here, which is the one I was just talking about. It returns true when a list's items are in order and false otherwise. That's all it does. Then I introduce this other really crazy function here called true. What does that do? It ignores its input and it just always returns true. Now, we flip the top arrow around because we can by taking its converse. And we do a little composition here, in this case relation composition. So the composition of these two relations gives us the set of all possible sorted lists. The set of all possible sorted lists, having nothing to do with our input list. Okay? So is this what we needed to complete our diagram? It actually is. So we'll combine this with our shared attribute to ignore lists that have different elements than our input. So it works. By following the metaphorism recipe, any sorting algorithm will basically obey this relational specification. Intuitively, what does it mean? A sorting algorithm generates a permutation of an input list, moves the elements around in such a way that in the output all the elements are in order. That's a specification for a sorting algorithm. Okay? This looks pretty good so far, but there's this thing up here. I hate that thing. It's that shrinking operator. Like, what do we do with that? Well, it turns out we can get rid of it. According to the papers that I've read, when our optimization criterion is a predicate postcondition, just like the one we were using, the shrink operator just reduces to a reverse relation composition. If I go to the previous slide, look up there. There's the shrinking operator. Now watch the left and the right side. I just flip them around and I compose. That's all that reduces to. There's a bunch of algebraic proof to show that, but it works out. So this here is a complete relational spec for a sort function. And even if you don't know a lot of what's going on here, you can kind of like walk through it and be like, yeah, that kind of makes sense. So now let's explore transforming that specification into a functional program. We're going to come up with an algorithm we're going to call mystery sort, which some of you are going to figure out what it is right away. Raise your hand when you finally figure out what we're talking about, what our mystery sort actually is. We're going to start with a divide and conquer template. We're going to plug in bits and pieces of our spec for sort one at a time, and then we're just going to turn the crank and see what falls out. So here is the relational spec from the earlier slides. First thing we have to do is dig out a hole in the middle where we're going to put our intermediate data structure, the cream and the Oreo kind of thing. Here we're going to use leafy trees in which the values are stored at the leaves of the tree. So all the values are at the bottom of the tree, and then this stuff up here is just for managing the topology of the tree. Okay. According to the easy divide hard conquer recipe, which we're going to use, easy divide hard conquer, it's okay. We need a function that will turn a binary tree into a list. So we'll call this function tips. All it does is it takes a binary tree where all the values are at the leaves, and it just plucks off the leaves one by one, stuffs them in a list. That's all it does. So now we have to figure out this function y, and then suddenly everything will take care of itself. And you'll have to trust me on this one. There's a lot of work which shows that that is what we need to plug in for y. So the paper is very generic. All I did is I plugged in the morphisms that I had, and this is what came out the other end. I wrote it in Scala and it worked. Okay, you'll have to trust me.
So bag takes a list to the bag of elements of the list.
Yes, yeah. So what is our mystery sort? We're getting closer. The function that satisfies y in that previous slide is actually the list merge that we see in merge sort. So our mystery sort algorithm that we came up with was actually merge sort. But we did it without even knowing how to do merge sort. Just fell out. Woo! Okay. Now here's something that's really neat. We just started with a spec. Yeah, go ahead.
How did you know you needed to use the tree in there?
I cheated.
Okay.
Yeah. I'm not a wizard with this stuff yet, you know. But supposedly, I don't know. I can't even make that claim. I don't know if this stuff is ready for prime time yet. You know, this is cutting edge. This paper came out recently, a few months ago or something.
Go back to that thing where you derived it.
This?
Yeah. So right there, we're starting with tips inverse, or tips converse, right? Followed by tips. So that takes a list of things, finds all of the trees that may have those, and then does tips again to it. So now we have the same list. Then it does bag, which puts them into a bag, and then does bag converse, which finds all of the bags that may have contained those. But so it's all of the sortings.
So it's all the lists.
All the lists
that
that
can be made out of the bag.
So why did we need tips at all? Why couldn't we have dropped tips converse and tips there?
That is a good question. And here's my answer to that. I felt that I didn't need to think about it because I took the paper and I just plugged stuff in and it worked.
So I guess if you go one more back, it seems like you could have used bag tree in the middle. I'm sorry, bag of tea in the middle. And then the lower half would just be.
Then maybe it's not merge, or yeah, maybe it's not merge sort.
I'll have to think about that.
Going to a tree is kind of what is actually.
But we're not using any of the structure of a tree in a merge sort. Right? We throw away all that information when we go to the back.
Well, it gives us the divide, I guess.
No, it depends on how you go from a list to tree. Like if you
But
do,
tips converse does all of the trees. Is the tree used for the partitioning of the list? Is that what it's doing? Is all the various ways of partitioning the lists?
The tree kind of represents the recursive calls in merge sort.
Okay, yeah, so it must be all the different partitionings of the list.
Yeah, you can think of it that way, yeah.
So that justifies use of tree.
I think if you just go through bag, it would just be like random sort.
Yeah, we just randomly
Yeah, it literally just
take
that's like the algorithm
elements
random
out
sort.
of it,
Just
yeah.
throw it in the bag, pull elements out until you get an ordered list.
Yeah.
So.
There's something cool about this conversation. There's a paper called Sorting Morphisms, which works through exactly this conversation we're having. And it shows you that by sticking different types in here, different inductive types, you implement different sorting algorithms. You can get insertion sort. You can get quick sort. Yeah. And depending on which side you do the heavy lifting, you know, in the divide phase or the conquer phase, you get a different sorting algorithm. It's pretty cool.
Default is a sort of magical sort where it's just, oh, it's sorted, but we don't. Because it's just non-deterministic.
Yeah.
Thank you.
So we have derived merge sort, and we know nothing about implementing sorting algorithms. And different choices lead to different sorting algorithms. So in conclusion, metaphors are everywhere, not just in your programming. They're happening all around you, and if you notice them, it's pretty neat. We can use them in programming. The Bird-Meertens formalism is pretty cool. Thinking of functions as relations kind of gives you a new eye-opening experience, because now you can flip things around and think backwards and do all other sorts of cool things. And you can keep climbing the ladder of abstraction, and there's more value at the top, you know? It just doesn't stop giving, which is pretty neat. And I would like to close, before I acknowledge my team, with this meta metaphor. Burning the candle at both ends might seem super neat, but I'll guarantee it's not the way to make our two ends meet. That would be very painful, right? So here's the research team I work with. This is me, and this was my boss. I actually got promoted after this. Lynn Conaway, she does research studies, usability studies and things like that, user research. And here are our two research assistants. Thank you very much. Any questions?
Do you have an example of turning this into code out anywhere that's publicly available?
It's not publicly available yet, but I did it. I took this DC3 skew algorithm for calculating suffix arrays, and I ran through this exercise, and I came up with a hylomorphism. And that's actually how I learned Matryoshka. A very small portion of Matryoshka.
Yeah, I mean, that to me seems like one of the most interesting steps, because otherwise you might just be defining a relational programming language, where you would, this would become the native syntax of the language, which would also be really weird, kind of cool.
Yeah, exactly. That's the cool thing, is you can start with a relational thing, and then a functional program pops out where everything's a function. It's pretty neat.
So is metaphorism a pun on metamorphism?
It might be.
Yeah, because the hylomorphism starts with a value, constructs a coalgebra, and then does the catamorphism back to the value again. Whereas the metamorphism goes the other way. You start with a structure, get a value, and then expand it again.
Exactly.
Swapped.
Yeah, and this has all those ingredients, but then you add the formal metaphor. So,
Yes, the metaphor.
yeah, yeah.
Now I understand why. Well, sort of understand why it's called a metaphor. At least if I can figure out that diagram.
Yeah.
What happens when you turn all the arrows around? What's
That's
the
a-
dual with this thing?
That's a good question.
Oh.
Oh.
Always ask.
Well-
Spans instead of cospans, and vice versa.
Yeah.
That itself is
Well. I'm going to reverse the other arrows.
There's a reverse Y.
If you just reverse the guy in the upper right corner, no, not even that. Remember, at the end of the day,
you've got a bicategory of cospans, and then you compose them using the span in the middle.
I have no idea. I know how to flip this guy around. Yeah, interesting questions. Anything else? Well, thank you for attending my talk. I appreciate it.